Okay, so we are moving to part three, which will talk about acids and bases and buffers. So there are several definitions of buffers, but the definition that we're going to be using here is the Arrhenius definition that states that any substance dissolved in water that hydrolyzes into a hydronium ion or a hydrogen ion is considered to be an acid. And any substance that hydrolyzes or dissociates in water and forms a hydroxide ion is called a base. So again, this is an acid. And how do I know it's an acid? Well, I can tell by this little H here, but I can also see that it dissociates into a hydronium ion and sometimes is abbreviated as a H plus. I know that this is a base, okay, because it releases this hydroxide ion. Okay, so that's how we know. So acids or the acidity or the basicity of something is measured using a pH, which is the negative log of the concentration of the hydronium ion. So looking at the scale here, the pH is a scale from 0 to 14, where, let me write it down, where 7 is neutral, okay? And as it shows in here, as it moves below 7, it increases in acidity, and it says right here, increase in acidity. As it goes below 7, it increases in basicity. And when I says increasing acidity, and when I say increases in basicity, what I'm looking at is the concentration is a ratio, right? So it's a concentration of the hydronium ion, which is the acid, to the concentration of the hydroxide ion, which is a base. At pH 7, they have the same concentration. As it moves below 7, the concentration of the hydronium ion is going to keep increasing, 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 and that's what leads to increase in acidity. As it goes below 7, the concentration of the acid would start to decrease, but the concentration of the base will start to increase and increase and increase. And it's just like I mentioned, I used this analogy before, it's just like a seesaw. If this is OH and this is H, okay, as one increases, the other one decreases. And at pH 7, you find them equal. Okay? And you're welcome to pause this video and look at the numbers, and you can see exactly what I've just said, but you can actually double check and see that you can understand that by just looking at the numbers. Right, so there are two things that will affect pH. Concentration, meaning the amount of either the base or the acid that's present. Right, we showed over here that concentration of the acid or concentration of the base will lead to different pHs. And then strength. So when we talk about strength, we're talking about how much of the acid or the base dissociates in the presence of water. Okay, and when I say dissociates, meaning that break apart. Right, if an acid does not dissociate, then it's not going to be relevant at all because remember the pH is the measure of H. So that H needs that acid or that base needs to be dissociated. Okay. So usually weak acids only partially dissociate or separate. Strong acids fully dissociate. So let's look at a few reactions here. So a strong acid, so hydrochloric acid in the presence of water will fully dissociate. So you can see here the hydrogen ion, which is what makes an acid an acid. And then its conjugate base. Here we have a weak acid, and the way we show that only partially dissociates is by showing this reversible reaction. Okay, so it is in a reversible reaction. This is the acid in the presence of water. This is its conjugate base, and this is the hydrogen ion. But it goes back and forth, back and forth. So it does not fully dissociate. The same thing can be said for the base. Sodium hydroxide in the presence of water, it fully dissociates. You can see here the hydroxide ion representing the base. And then ammonia over here, which is a weak base, it releases hydroxide ion as well, but again, it doesn't fully dissociate, so the reaction is reversible. Okay. It is important to note that when an acid and a base come together, they form salt and water. Okay, always, and it's called a neutralization reaction. Okay, the components of what make an acid, or what makes a base is what forms the water. So the H comes from here and the OH comes from here. Anything else remaining is going to be the salt. When I talk about the salt, we're talking about an ionic compound, any compound with a metal and a non-metal. And then we need to talk a little bit about equilibrium so we can better understand weak acids or weak bases. So let's focus on this, guys, the weak acid and the weak base. So for that, we need to review a little bit about equilibrium. So under equilibrium, okay, the reaction is reversible. And we say that something is in equilibrium, or reaction is in equilibrium, when the rate, the speed of the forward reaction equals the speed of the reverse reaction. Okay? So when the rates of the forward equal the rate of the reverse, it says that it has achieved equilibrium. Okay? Now that equilibrium can be disturbed. So let's talk about what happens when that equilibrium that's nice and happy gets stressed. Well, that what comes in Le Chatelier's principle. If a dynamic equilibrium is disturbed by changing the conditions, the position of the equilibrium, or it means the rate, moves to counteract that change. Okay, so it's all about counteracting the change so equilibrium can be returned. So we use this cheat sheet here over here to figure out how the reaction will counterbalance. Right, so let's look at an example. So this is a reaction, and it's not an acid and base. Yeah, so let's start without the acid and base for now. Let's just look at a regular reaction. I know it's not an acid and base because, well, I don't see an acid and I don't see a base, right? So what will happen to the equilibrium when the concentration of H increases? Well, first thing you need to do is to find H. H is right here. Okay. So concentration of H is increasing. Okay, so again, because this concentration of H is increasing, the equilibrium will counterbalance. In other words, the rate of the forward reaction will pick up, will increase. So that way all this H gets used up and the reaction can return to equilibrium. So the direction of the equilibrium at the beginning will shift quite a bit forward so that the H can get used up and the reaction can return to equilibrium. Okay, um, the same is true if this decreases. Okay, um, water is going to begin to decompose much faster so that the reaction can return to equilibrium. Okay, so that is one way to approach this kind of problem, is just by looking at counteracting. How can equilibrium counteract so that it can return to its original position? The other way, let me erase this. The other way to approach this is by using that sheet that I gave you, which be aware that it's not an open note test, so you need to figure out a way to memorize it. That's why I prefer this method, because it requires no memorization. But you need to figure out a way to memorize it if you are relying on this. Right. So let's use this to solve this other problem. So what happens to the concentration? What happens to equilibrium when the concentration of oxygen increases? Well, the first thing you need to figure out is oxygen a product or a reactant? In this case, oxygen is a reactant because it's on this side of the equation. And is that increasing or decreasing? It's increasing. So then using that sheet, I look and I find a reactant that's increasing. The equilibrium will shift to the right. Okay, so reactant increasing shifts to the right. Reactant decreasing shifts to the left. So using this sheet, I can say, hey, based on that sheet, it will shift to the right when it's increasing, it will shift to the left when it's decreasing. Okay, and then let's do one more. Instead of concentration of water, I'm going to do temperature. Okay, so let's do, oops, let me write it down. Let's do temp. Okay, and then in here, let's do temp. So what happens to the equilibrium when temperature increases? Well, you have to look at whether it's an endothermic or exothermic reaction. Well, if heat is being added, it's endothermic. If heat is being released, it's exothermic. In this case, this reaction is exothermic. So you're going to treat it the same way as you treat it if it was a reactant or a product. It is a product. Okay, so this is increasing. The way to counterbalance is to shift the reaction this way. So the energy begins to get used up and slow down and cool off, right? So the reaction will shift to the left if heat is increased. Now, if heat is decreased, okay, the opposite will happen. The reaction will shift this way, so more heat is generated and can return to its original state. Okay, so that is equilibrium. So when we talk about buffers, a buffer is a system made up of weak acid and its conjugate base, or weak base and its conjugate acid. A buffer resists to pH change by reacting with added acid or base and shifting the equilibrium position. So in this case here, the acid and the base will be the stressors to the buffer. Okay, so that's how a buffer resists pH changes. When enough acid or base is added, the buffer will reach its capacity, and then the pH will just drastically change. So a buffer is not an infinite way to control pH. It has limitations. That's what I wanted to emphasize. All right, so here's an example of a buffer. Okay, so this is an acetate buffer. Okay, I know it's a buffer because it's a weak acid. I know it's an acid because there's a little H here, and it's in equilibrium. So if acid is added to this buffer, okay, let's talk about if it wasn't a buffer. If this was just a regular reaction and I added some acid to it. Okay, I just went ahead and I added some acid. Oops, right here. The pH will drastically drop. Okay, drastically drop. Okay, no buffer. Well, because the concentration of hydronium ion will just increase, right? There's not much to it. It will just increase. Okay, that's with no buffer. But because it's a buffer, the concentration will just slightly, the pH will only slightly change. In this case, it will only slightly decrease. And the reason for that is as soon as acid is added, the concentration of this would increase. Concentration of this would increase, and the equilibrium will shift this way. So the hydronium ion will begin to get used up. And when it begins to get used up, the pH will not be drastically changing because it's getting used up. Okay, so the equilibrium will shift this way, so the concentration of hydronium ion will become lower. Okay, so that's how you resist pH. The same is true if you add a base. Let me remove this here and say I added a base. Well, if I added a base, okay, so if I add OH here, well, the OH is going to shift the equilibrium this way. Okay, and it's going to shift the equilibrium this way because you become a neutralization reaction where you have an acid and a base, and you just produce its conjugate base. Okay, so you can think of an acid as shifting the equilibrium this way and a base as shifting the equilibrium this way. So the same way the pH will not drastically change because this reaction will cause a shift in equilibrium to happen. So you won't see that translated into a pH measurement. Okay, so that is that for this unit. Not for this unit, for this topic. Now we'll begin to look at how carbon dioxide in the atmosphere is affecting both climate change as well as ocean acidification. So we're going to be looking at applications now.